Let's see if we can apply some pseudocode to this algorithm, because it's one thing to sort of talk about it, and it's one thing to sort of reason through it intuitively. But at the end of the day, if you want to program this, we've got to be more precise, and we've got to consider the lower level operations that the computer thinks is going to execute. So here's how we might implement bubble sort. Repeat until no swaps. For I from 0 to n minus 2, and n is just the size of the problem, the number of doors, the number of humans, the number of numbers, whatever the input to the problem actually is. So for I from 0 to n minus 2, if the ith and the ith plus 1 elements are out of order, swap them. So this is kind of a mouthful, but if you think about it, I'm just kind of applying some of the vocabulary that we have from C and kind of sort of from scratch to an otherwise very organic human experience, but using more methodical language than I was just kind of doing off the cuff when we were doing it with humans. Because what does this mean? For I from 0 to n minus 2, that means start at like the 0 location. And if there's n elements here, this is 0. And this at the very end is location, it's going to be n minus 1. Right? If you start counting at 0, you have to readjust your whole life to subtract 1 from the tail end of those range of numbers. Right? Zeros, if that was 1, this would be n. But if that were 0, this is now n minus 1. So I'm saying, though, for I from 0 to n minus 2, which is technically this. So I'm using sort of for loop-like language to start iterating here and do something like this up until the second to last element, which we've not done before. Seems almost buggy. But if you read ahead in the pseudocode, why did I do that? And only iterate until the second to last element with I. What jumps out at you? Yeah?
Because then you're going to swap the I from the I plus 1 element.
Good.
When you get to n minus 2, you'll swap it with n minus 1.
Exactly. Recall that bubble sort was all about swapping, or potentially swapping, pairwise elements, neighbors, if you will. So you have to make sure that if you're iterating through all of these numbers, you have to stop short of the end of the array so that I plus 1 actually refers to an element that's actually in your list, and not, for instance, way over here, which would be some garbage value that you shouldn't actually touch. So if those elements are out of order, we swap them. And I have a big outer loop there that just says keep doing this again and again and again until you don't swap anything, at which point you can infer that you're done. Because every time I walked back and forth on the list and the guys helped out by swapping their numbers as appropriate, I kept doing it again if there was still room for improvement. And intuitively, why is it absolutely logically safe to stop that whole process once you have not made any swaps on a pass through the list? Why is that a safe conclusion? So if I walk through the list, no, these are good, these are good, these are good. OK, you didn't want your number. These are good, these are good. How do I know that I don't need to do that again? It's sorted already, right? It would be kind of irrational if you've walked through the list looking at everything pairwise, found nothing to swap, to even bother doing that again. Why would you expect different results if the numbers themselves are not moving and you didn't move them yourself? So you can just stop. But this still is going to invite the question, well, how expensive was that? How many swaps or comparisons did we make? And we'll come back to that before long. Selection sort, though, can be expressed maybe even a little more succinctly. And that was the second algorithm we did with our 8 volunteers here. For I from 0 to n minus 1. So this time, all the way through the end of the list, find the smallest element between I and n minus 1. So between those two ranges, the beginning of your list and the end. And then swap the smallest with the ith element. So what does this mean? So again, for I from 0 to n minus 1, this is just pseudocode for saying start a variable I at location 0. And do this until I equals n minus 1. So do this until you've gone all the way through the list. What is it telling me to do? Find the smallest element between the ith element and the end of the list. N minus 1 never changes. It always refers to the end of the list. So that's why I walk through the list looking for ultimately the number 1. And what did I do with the number 1? Swap the smallest with the ith element. And I might have gotten one of these steps wrong when I did a little switcheroo, but we fixed it thereafter. Ultimately, I kept evicting whoever was in the ith location to make room for the element that I knew belonged there. And I could have shuffled them to make room for those elements, but it turns out mathematically it's just as fine to just evict it and move it all the way to the end as we did. And once I've gone all the way through the list, there's no more smallest element to find, and as we saw, the list is sorted. So maybe this is faster, maybe this is slower. It's not immediately obvious. An insertion sort, which we actually came up with by way of the blue books on the floor, might be described as this. For I from 1 to n minus 1, call the 0th through I minus 1th elements the sorted side. That's a mouthful. So consider the left of your list the sorted side of the list. And initially, there's nothing there. You have 0 elements sorted to your left and 8 unsorted elements to your right. So that sort of describes this story when we had volunteers and numbers here. There are no elements sorted. Everything to my right was unsorted. That's all that's saying. Remove the ith element. That was like picking up this blue book, if we were using blue books in this example. Then what do I want to do? Insert it into the sorted side in order. So if this is the sorted side, this is the unsorted side, this is the equivalent of saying take that blue book and just put it in the first location. And you can kind of make a visual gap for it. Now this is the sorted side. This is the unsorted side. Or equivalently, when I was down here with the blue books, the books in my hands were the sorted side, and everything still on the stage was the unsorted side. Same idea. So what happens next? I then iterate one location next, and I remove the next element. And whatever number that is, I figure out, does it go to the left or does it go to the right? Which was the same thing, again, on the stage, me sort of picking up a third blue book and deciding, does it go in between these books? Does it go below? Does it go above? I inserted it into its appropriate location. So in this insertion sort algorithm, you sort of take each number as you encounter it and deal with it then and there. You take the number and deal with it. So you know what? This one's got to go here, if we just kind of pretend what the numbers look like for a moment. So that would be inserting it into the right location, like I did with the blue books. Maybe this one, maybe this one's a really small number, and so I insert it over here. So I kind of literally deal with each problem as I encounter it. But it just gets expensive or really annoying to have to like move all of this stuff out of the way to make room for those elements. And that's why I got bored with the blue book example, because it was getting very tedious looking through all of the blue books for the correct location. So in short, all three of these algorithms, while very differently expressed, and while all of them are kind of intuitive until you try to describe what your human intuition has actually been doing for the past some number of years, that you've been sorting things just for in the real world, they can all be described at least in terms of these algorithms. So these algorithms, and we started this conversation in the first lecture, all have ultimately some kind of running time associated with them. Like how long does it take to do something? And we talked about the process of finding Mike Smith in terms of this pretty generic graph. It wasn't very mathematical, it wasn't very sophisticated. We just wanted to get a sense of the relationships or trade-offs of space and time, so to speak. And so on the x-axis or horizontal, we had the size of the problem, so like number of pages in the phone book or number of people in the phone book. And on the y-axis or vertical, we had the amount of time to solve the problem. How many seconds, how many page turns you could count using any unit of measure you like. And the first algorithm for Mike Smith, when I started with the very first page and turned and turned and turned, was a straight line, linear relationship. One more page, one more step. So it's straight line. The next algorithm was searching by twos, recall, in the first lecture. 2, 4, 6, 8. And that's still a straight line because there's a predictable relationship between number of pages and number of seconds or page turns. It's 2 to 1 instead of 1 to 1. So it's still a straight line, but it's lower on the graph. It's better. But the best one by far was the divide and conquer approach, we said, right? And it certainly felt faster. It's great because it was intuitive. It wasn't quite as easy to express in pseudocode. That was among the longer ones today. But it at least got us to the answer faster. And this is logarithmic in the sense that the logarithm, technically base 2 if you recall some of your math, it's because you're dividing the problem in half and half and half. And it's fine if you're uncomfortable with it, don't even remember what a logarithm is. For now, just assume that logarithmic time has this different shape to it. It grows much more slowly. Anytime you can choose log of n over n when picking between two algorithms, go with the log n or something like that, because it is going to be smaller, as we can see visually here. So let's just consider something like bubble sort. There's a couple of ways we can look at this. And again, the goal here is not to be very mathematical. We're not going to start doing proofs. But at least by taking a glance at some of the steps in this algorithm, you can get a general sense of how slow or how fast an algorithm is. And indeed, that's the goal. There's this fancy notation we're about to see called asymptotic notation with special Greek characters. But at the end of the day, we're really just trying to get an intuitive sense of how good or bad an algorithm is, much like we were trying to do with this picture. But now we'll do it a little more conventionally as a computer scientist might. So in bubble sort, recall that we compared every pair of humans and made a swap if they were out of order. And then we repeated, and we repeated, and repeated, and we kept going through the list. So that can be quantized. Like you can kind of break that down into some total number of steps. So if you've got n humans in front of the room and you want to compare them from left to right in pairs, how many possible pairs are there as I walk through the list for that first time? If there's n elements, and I can put the stands back where they were, how many pairs were there as I walk from left to right? I compared these two, these two, these two. Yeah, there's n minus 1, right? It's specifically 7. And even if you're not quite sure where we're going with this, if there's 8 stands, like this is 1, 2, 3, 4, 5, 6, 7, and there's 8 total, so that's indeed n minus 1. So that's how many comparisons we might have made the first time through bubble sort. But the very first time I went through the list in bubble sort, did the list get fully sorted? No, we had to do it again. We knew that 8 had bubbled up to the very end, so that was good. 8 was in the right place. But I had to do it again and fix more problems along the way. But the second time, I didn't need to go all the way through the list. To be clear, who did I not need to look at? The last location, or 8 in our very specific case. So the second time through the list of humans, I only have to make n minus 2 comparisons, right? Because I can just ignore number 8, the final human, and just deal with the 7 other humans that are somehow misordered. So if I wanted to really be nitpicky and write this down and count up how many steps or how many comparisons I made, we could kind of generalize it like this, right? It's going to be n minus 1 plus n minus 2 plus n minus 3 plus dot, 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 or more specifically, 7 plus 6 plus 5 plus 4. This is just a fancier formulaic way of saying the same thing. Now, I don't remember my back of math book formulas all that well, but I remember this one. You know, in your physics books or your math books, often in the hard covers, you'll see little cheat sheets for what series of numbers actually sum to or multiply out to. And so it turns out that that summation can actually be expressed more succinctly as n times n minus 1, all divided by 2. That is the same thing mathematically as the long series that I had a dot, dot, dot there for. So if I multiply this out, just using some algebra, that's like n squared minus n divided by 2. And then if I kind of multiply that out, that's n squared divided by 2 minus n over 2. So if I wanted to be really precise, this is the running time of bubble sort. It takes this many steps to sort n people. Why? Because I literally just counted the number of comparisons I made. That's how many comparisons it takes to do bubble sort. But honestly, this is really getting tedious, and my eyes are already starting to glaze over. I don't want to remember these algebraic formulas here. So let's actually try an example just to get a sense of how slow or how fast this is. Suppose that n were 1,000,000. So not 8, but 1,000,000 people or 1,000,000 numbers. How slow or fast is bubble sort going to be? Well, if we plug in 1,000,000, that's like saying n is 1,000,000. So that's 1,000,000 squared divided by 2. Minus 1,000,000 divided by 2, because that's what it all summed up to be. So if I do this out, it's a really big number, 500 billion minus 500,000. And in any other context, 500,000 is a pretty darn big number. But not so much when you subtract it from 500 billion, because you still get 499,999,500,000 after subtracting those off. Which is to say, of those two terms, the one on the left versus the one on the right, which is the bigger one, the more dominating factor in the mathematical expression? It's the one on the left, right? That's the one that's massively bigger. And so more generally, n squared divided by 2 feels like a bigger result than n divided by 2 alone. And we've seen it by proof by example, which is not a proof, but it at least gives us a feel for the size of the program or the number of comparisons we're actually making. So you know what? If that is the case, if the dominant factor, the one on the left in our case, the one with the square specifically, is just so much more influential on the number of comparisons we're going to make, then let's just wave our hands at the lower ordered terms, n divided by 2 and anything like that, and just say, this algorithm feels like n squared. I'm going to throw away the denominator. I'm going to throw away the thing I'm subtracting off. I'm going to throw away anything that is not the dominating factor, which is the term that contributes the most to the total number of steps incurred. And indeed, this is what a computer scientist would describe generally as the running time of this algorithm. It is on the order of n squared. It's not n squared, but it's on the order of n squared, as we've seen. It's pretty darn close, and that's good enough for a conversation with another reasonable person who wants to debate whether his or her algorithm is maybe better or worse than yours. So this would be called big O notation. Big O is used to refer to an upper bound on an algorithm's running time. Upper bound meaning, we'll consider, for our purposes, in the worst case, how much time might this algorithm take? Well, it's going to take on the order of n squared steps. Because if the list of numbers is unsorted initially, we got to do a lot of work to actually sort it. There's other terms that we could put in those parentheses. Some algorithms are not n order of n squared. Some algorithms are actually order of n log n. Some algorithms are on the order of n itself, or log n, or even 1, where 1 refers to constant time. And in fact, the ones I've highlighted here, we've actually seen examples along the way of all of these so far. For instance, what algorithm have we seen that has a running time on the order of n steps? Linear search. If we think back even to today, to linear search, or from the first lecture when I was just looking for Mike really slowly, one phone book page at a time, that's a linear algorithm. If there's n pages or n humans, it might take me on the order of n steps because Mike Smith, S is toward the end of the alphabet, so he might be way over there or way toward the end of the phone book. Or God forbid his name starts with a Z, then I'm really going to have to go all the way to the end of the phone book. And so that's on the order of n steps. So n here would be linear. We've also seen another algorithm here in yellow, big O of log n. Saw it just a moment ago. Which of our algorithms was on the order of log n running time? Yeah, so binary search, divide and conquer. We didn't call it, we didn't describe it this formulaically in the first lecture, but that's how you would describe the running time, not just with a pretty picture, but just with an expression like this that all humans, at least computer scientists, can agree upon. And constant time. The funny thing here is because we're throwing away terms that don't really matter, O of 1 does not mean an algorithm that takes one step only. That would be a very limited number of options for your algorithms. But it does mean, symbolically, a constant number of steps. A constant number of steps. So what's something you might do that takes a constant number of steps in an algorithm? Maybe in like the first lecture, we had the silly peanut butter and jelly example. Which of the steps that day might have taken big O of 1 steps, a constant number of steps? I remember one like insert knife into jar. Like that's kind of 1 step. Maybe it's 2 because I might have to like pick up the knife and insert it into the jar then. 1 step, 2 steps, but it's a constant number. The number of steps is not at all informed by the algorithm itself. It just happens. You do that in 1 step.